Let's talk about the ground we walk on every day. Seriously, have you ever stopped to think about it? How in the world does a solid chunk of rock turn into, well, dirt? It's this incredible slow-motion story happening all around us, the story of how a mountain becomes mud. So, yeah, let's dig in.
I mean, it's a huge question when you really think about it, right? We look up and see these massive mountains, and then we go to the beach and see tiny grains of sand. But the journey between those two, that's a whole epic tale of destruction and creation. And the wild part is, it's happening right now, silently, all around us.
Here's a great way to wrap your head around it. Think of it as the slow, steady rusting of our planet's crust. It's a perfect analogy, really. Just like a piece of iron starts to rust when you leave it out in the rain, the minerals that make up rocks are perfectly happy and stable deep underground. But bring them up to the surface, expose them to air and water, and they just aren't stable anymore. They start to break down, they start to change, and that whole process, that's what geologists call weathering.
Okay, so here's the plan for our journey. We're going to start with the very beginning, how rocks first start to decompose. Then we'll get into the nitty-gritty of the chemical and physical beatdown they endure. After that, we'll look at what happens to all the broken pieces, how they get moved around and sorted. Then we'll see the grand finale, the birth of soil itself. And to wrap it all up, we'll see why any of this matters, what the soil can actually tell us.
All right, first up, decomposition. So, picture this. You have a rock. It was born under insane amounts of heat and pressure, miles beneath the Earth's surface. That's its home. Now, imagine that rock suddenly gets shoved up to the surface. It's hit with air, water, plants, animals. It is a complete and total shock to its system.
This process, weathering, it's really like a 1-2 punch. On one hand, you've got the physical forces, the brute strength just smashing and cracking the rock into smaller and smaller bits. But at the exact same time, you've got this silent, invisible chemical attack going on, which actually changes the minerals themselves. They are just not built for this environment. They're fundamentally unstable up here.
So when this whole breakdown is done, you're left with three main things. First, you've got dissolved stuff. Tiny charged particles, ions, that just get washed away by water, kind of like salt dissolving in the ocean. Gone. Second, you have the leftovers, the tough guys that survived the fight. This is your residuum, things like quartz that just don't break down easily. And finally, you have brand new materials that were created during the fight, stable things like clay minerals and iron hydroxides.
Okay, now let's zoom way in. Let's talk about the chemical takedown. This is the sneaky, invisible part of the story. The attack that happens on a molecular level. It's slow, sure, but it's relentless. And it's how you turn a hard rock into soft clay.
So, what's the main weapon in this chemical war? You might be surprised. It's rainwater. Yep, just plain old rain. See, as rain falls through the sky, it picks up some carbon dioxide from the atmosphere. This makes the water slightly acidic. I mean, we're talking super weak. It's not going to hurt you. But give it a few million years, and that slightly acidic water is powerful enough to dissolve entire mountain ranges. It's wild.
Let's take a look at a real-world example. Meet feldspar. It's one of the most common minerals on the entire planet. So, what happens when our acidic rainwater hits it? Well, a chemical reaction called hydrolysis kicks into gear. And that feldspar, it starts to completely transform. I mean, right now, as we're talking, billions and billions of tons of feldspar are slowly, quietly turning into clay.
And just like that, the original feldspar is toast. It's gone. Some of its parts, like potassium and silica, just dissolve and get carried away by groundwater. But what's left behind is something totally new and, importantly, stable in this environment. A clay mineral called kaolinite. Think about that. A hard, solid crystal has literally been transformed into soft clay and a bunch of dissolved bits. So, while all that sneaky chemistry is happening at the micro level, don't forget about the other side of the attack. There's also a straight-up brute force approach going on, physically ripping these rocks to shreds. And here's the kicker. These two attacks, the chemical and the physical, they're a team. They work together. Here's a simple way to think about it. Imagine dissolving a sugar cube in your tea versus a spoonful of loose sugar. Which one dissolves faster? The loose sugar, right? Because it has way more surface area exposed to the water. Physical weathering does the exact same thing to rocks. It smashes them into smaller pieces, which creates a ton more surface area for that acidic rainwater to work its magic. It's a feedback loop. And the culprits doing all this physical smashing? Oh, they're everywhere. We're talking about the unstoppable power of a glacier carving out a valley,
Or something as simple as water seeping into a crack, freezing, expanding, and splitting the rock apart. Even a tiny tree root, just slowly and steadily growing, can pry a massive boulder in two over time.
Okay, so our rock is no longer a rock. It's been broken down into a jumbled mess of smaller particles. Sand, silt, clay. Now the next chapter of the story can begin, sorting and moving.
In this phase has a name you've definitely heard before, erosion. The best way to picture erosion is like a massive, natural sorting machine. All the forces that carry this broken down material away, water, wind, ice, gravity, they don't just pick it all up in one big pile. Nope, they sort it, separating all the little particles by their size and their weight.
Now, not all of these sorting machines are created equal. Gravity and ice, they're kind of sloppy. A landslide or a glacier pretty much just picks everything up and dumps it in one big, disorganized mess. Water is a little more organized. It's pretty good at separating sand and leaving it on the beach while carrying the finer mud further out. But wind is the master sorter. It is incredibly precise. It can be so selective that it only picks up grains of a specific size, leaving behind these vast deserts of perfectly uniform sand.
This whole process is also a story of survival of the fittest, mineral style. Different minerals break down at totally different speeds. You have something like olivine, which is super unstable on the surface and weathers away really fast. But then you have quartz. Quartz is the ultimate survivor. It is unbelievably tough and resistant to weathering. And that is why, after millions of years have turned almost everything else into clay, our beaches and deserts are covered in all that beautiful quartz sand.
So we've got all this broken down, sorted, and moved material. What happens next? Does it just sit there in a big pile? Nope. Over time, something amazing happens. It starts to organize itself. It forms these incredible, complex layers that we call soil.
Take a look at this. This is what we call a soil profile. And it's the ultimate proof that soil isn't just dirt. It has a structure, an architecture. Each one of these distinct layers, geologists call them horizons, tells a different part of the story, from the rich, living topsoil all the way down to the solid rock where it all began.
Let's take a quick tour from top to bottom. Right at the top, you've got the A horizon. That's your topsoil, full of organic goodies and clay. Dig a little deeper and you hit the B horizon. This is where a lot of that clay from above ends up. Go down further and you're in the C horizon. Now we're talking. This is basically partially crumbled bedrock. You can still see chunks of the original rock here. And finally, you hit rock bottom, the D horizon. That's the solid, unweathered bedrock, the very start of our story.
Okay, so why should we care about any of this? Why does this whole rock-to-dirt story matter? Well, it turns out that being able to read the soil is a huge deal. It has massive implications for us, affecting literally everything from the food on our plates to the houses we live in.
Think about it from an engineering perspective. The kind of rock the soil originally came from creates very specific problems. If your soil came from granite, for instance, it might be prone to collapsing or washing away. If it came from shale, you'd better be worried about building on a slope. A good engineer who understands the local geology knows exactly what to watch out for before they even stick a shovel in the ground. It's not just about what rock it came from, it's also about how it got there. Was it transported? That loose junk that gravity just dumped on a hillside. Yeah, that's a potential landslide. That superfine soil that the wind dropped off? It could literally collapse the first time it gets really wet. Every single soil has an origin story, and for an engineer or a farmer, each story presents a completely unique puzzle to solve.
So next time you're outside, just take a second and look down. The ground you're standing on, it's not just dirt. It's a history book. It's the final chapter of this incredible, ancient story of chemistry, physics, and time. And the cool part is, now you know how to read the first few pages. So it makes you wonder, what story is the soil beneath your feet telling?